Okay guys, a little bit of a different video. I already pre-annotated it, having a little bit of technical difficulties at home. So for this first problem, STP, you could just do it like a normal stoic problem with PV equals nRT, but instead it's easier if you use the relationship that any gas at STP is has a volume of 22.4 liters for every 1 mole. So in this problem, you have 0.1 grams of magnesium, and they want to know volume of hydrogen gas. So we convert the grams of magnesium to moles of magnesium, the moles of magnesium to moles of hydrogen gas, and we have two options. We can put it right into PV equals nRT using 0 degrees Celsius and 1 atmosphere, or we could use this relationship. For every 1 mole, there's 22.4 liters. Doing that gives us 92.1 milliliters once we multiply our answer by 1,000. In this case, we have 1.5 grams of CH4 and 1.5 grams of O2 from the balanced reactant. Well, this is a typical limiting reactant problem. We're going to take those 1.4 grams of methane, convert them to moles of methane, use the mole ratio to convert to moles of CO2, and we could plug right into PV equals nRT to get liters. But instead of doing that, we could use the relationship that 1 mole of any gas at STP is 22.4 liters. We then convert the oxygen, 1.5 grams of oxygen. There's 32 grams of that per every 1 mole. There's 2 moles of oxygen per every 1 mole of CO2 per the mole ratio, and we could plug that right into PV equals nRT, the rearranged version V equals nRT over P, using 0 degrees Celsius and 1 atmosphere, or we could use the relationship at STP that every 1 mole is 22.4 liters. One of those answers is going to be smaller than the other, and that's going to be your answer. 0.5, I believe, is the answer. Next question, moving on to kinetic molecular theory. We know that the theory says that all the temperature of any gas is directly proportional to its kinetic energy. It says that the gas particles, their volume is negligible compared to the size of the container. It says that attractive forces are minimal, and it says that they're constantly moving, and we like them to be moving. So the kinetic molecular theory predicts that at a given temperature, that should tee you off that the answer should relate to the kinetic energy. We know that D is tempting, but they don't all move at the same speed. Actually, the heavier molecules move at a lighter or a slower speed. Ideal gases, well, which things fit the postulate? Have no volume. We assume that, not true though, but we assume that with the kinetic molecular theory. And we assume and see that they have no attractive forces. Now we know that's fake, right? And that's really the difference between real gases and ideal gases. But that assumption allows us to use PV equals nRT. And in using PV equals nRT, we can approximate the behavior of all gas particles. Under which conditions would a real gas, a normal gas, behave the most ideal? Well, if we want it to be ideal, we want it to move around and expand. So we want the pressure really low, so they have room to expand, and we want their temperature really high, so they're moving real fast. For this free response problem, A, which molecule is most likely to be a gas at room temperature? Well, that's going to be methanol, the one here on the right. It's going to be most likely to be gas because although they're all polar and they all exhibit London dispersion and dipole-dipole forces, methanol is not strengthened by hydrogen bonding. Thus, its attractive forces are the weakest, and it's most likely to be a gas. This next problem says, if at 300 K each molecule above is in the gaseous phase, which molecule has the greatest speed? Well, according to KMT theory, they all have the same kinetic energy, but lighter particles have to be moving at a greater speed to have that kinetic energy. Methanol is the lightest with a molar mass of 30 grams per mole. Moving on here to the next problem. The following questions pertain to the gas in the 2 cylinders above. Compare their kinetic energies. Well, they're both at the same temperature, so according to the KMT theory, they both have the same kinetic energy. Which gas deviates more from the ideal behavior? So which gas is really more real? Well, they're both nonpolar, so this is kind of tricky. But nitrogen is a bigger gas. So the London dispersion forces between the nitrogen particles are strengthened by their increased polarizability, making the attraction between the neighboring particles greater. And if you have more attraction between the particles, that gas is going to be less ideal. Moving on here to number 3. Which of the following pairs are inversely proportional to one another? Now, according to our PTV stick, we know that T and V and P and T are directly related to one another, but P and V are inversely related. So A is the answer, but let's double check. We know that T and kinetic energy, temperature and kinetic energy, are directly related to one another. They relate to one another. What we mean by that is when one goes up, the other goes up. Volume and moles have the potential to be directly related to one another when pressure and temperature are held constant, and volume and temperature have the potential of being directly related to one another. Only pressure and volume are inversely related. It makes sense. If you squeeze on something, it's going to get smaller. This next problem is really cool. It asks for 3 methods to make the volume of that flexible balloon increase. So we could do one thing. We could simply keep P and T constant and we could blow into the balloon. That would make it bigger. That's the way we've been doing it our whole lives. So that's the relationship between moles and volume. Another way is we can keep the moles inside constant and the temperature constant, and we can bring it to a higher elevation like we did in the vacuum chamber. That would drop the external P, which would increase the volume. And the third one, we could keep the moles and pressure constant, keep that balloon flexible, and do like what we do with a hot air balloon. We could increase the external temperature. Only method 2 really leverages that inverse relationship. Question 4, ideal gas calculations. This question is asking for the molar mass of a gas. Now it seems kind of tricky because we don't know what gas it is. But all we need to do is rearrange our equations here. So the molar mass of a gas can be derived the following way. We know that molar mass is grams per mole. And we know that molar mass of a gas could be determined by saying grams per N. And we can rearrange N using PV equals nRT to be PV over RT. Rearranging this denominator by multiplying by the reciprocal, we get the molar mass of a gas is equal to GRT over PV. We plug in 3.3 for G, 0.0821 for R. We add 150 to 273 and we get 423 for T, divided by 1.25 for the atmospheric pressure given, and 2 liters gives us the answer of D, 458. 273, 373 plus 50 is going to be 423. That's how you got the temperature. This next question is your typical mixed gas problem. Determine the total pressure in the cylinder. Well, we got it going on here. All we have to do is convert helium by dividing it by 4 to moles, convert nitrogen by dividing by 28 to get moles, add up the moles of helium and the moles of nitrogen, multiply by RT, divide by V, and we got the volume there at the total pressure of 5.49 atmospheres. Now that we got the total pressure, we can get the partial pressure of nitrogen. One of 2 ways. We could simply do PV equals nRT again and just use the moles of nitrogen, or we could use this equation. The mole fraction of nitrogen multiplied by the total pressure is 1.86 atm. Moles of nitrogen divided by total moles times the total pressure gives us 1.86 atm. Describe what would happen to the pressure inside the cylinder if the gas were cooled. Well, we're going to assume that the volume is constant and so are the number of moles, and if we rub some ice on that cylinder like we did in class, the pressure inside should decrease. Thanks a lot.